Okay, so let's apply the definition of the angular momentum to a few simple problems just to find the angular momentum. So the first problem is where we're going to find there's a particle of mass m moving with speed v parallel with the x-axis, and its distance from the origin is simply y, and we're going to find the angular momentum of this point about the origin. So we're going to find this. Now, in order to do this, we'll use both the definitions. We'll use the first definition first and the second definition, which is rp sine theta and then r cross p, and figure out the angular momentum. Okay, once again, the direction of the angular momentum is obtained by simply the right hand rule. Alright, so you take r and you turn it into p, and that's what you get. So in this case, about the origin, the angular momentum, okay, would be pointing along the negative y direction. It will be pointing into the plane of the paper, which we denote by the symbol x. Okay, so that's where the angular momentum would be pointing into the plane of the paper. Just check that out, make sure that you know it. Okay, let's find the magnitude though. So, and we'll do the magnitude by using both methods. We'll use rp sine theta first, and then we'll use r per p, and we'll figure out, both of them should give us the same answer. We'll see which one's easy. You decide, you be the judge. So rp sine theta first. So in order to do this, what we need to find the distance of the angular momentum first, okay, from the origin. Okay, so what we'll do is let's just call this angle theta, and if this angle is theta and if the y displacement is y, then the hypotenuse here ends up being equal to y divided by sine theta. Okay, so the angular momentum will be equal to y over sine theta, which is r, okay, multiplied by the momentum, which we know is simply m times v, and then multiplied by the angle that the two make with each other. So if we were to extend this line, okay, this angle would be nothing but pi minus theta. Alright, because if this angle is theta, then we know that this angle would be theta. This would be pi minus theta. So we could use either angles. We could either use sine of theta or sine pi minus theta. It doesn't really matter, because sine of pi minus theta is nothing but sine theta, and so this ends up being equal to mv times y. Okay, now let's see if we could have concluded the same thing by using the perpendicular distance relation. So if we have that, L is what is the perpendicular distance of the momentum from the origin. If you were to extend this line, you see that this distance is simply y. So my L is equal to y times mv, r per times mv. So you can just rewrite it as mvy. Okay, so a simple way of finding the angular momentum. Now we will be doing cases where we'll find the angular momentum for objects moving in. Okay, and so let's say that I have an object that's moving in a circle in a counterclockwise sense. Let us say that its velocity is v and its mass is m, and it's at a distance r from the center. Okay, and as this moves in a circle, we're going to find its angular momentum. Now here, there's no reason to use anything other than r per times p. But if you see, sine theta is also equal to 90, so I guess both definitions give you the same thing. So the angular momentum here is simply equal to m times v times r. Okay, this is another example that's simple. It keeps coming up a lot. It's something that we need to make sure we understand. Okay, in the next video, what we'll do is we'll see that angular momentum can also be written in terms of the moment of inertia. And then, once we have that, it gives us a few more, because when we look at systems of particles instead of just a few particles, it gets a little more tedious to write this MVR for each of the particles. So we could do this in terms of the moment of inertia. So that'll be the topic of the next video.